Example, compound cylinder problem N. This example. We analyze a compound cylinder formed by shrink fitting two thick cylinders together. The objective is to determine the final stress distribution across the cylinder when it is subjected to internal fluid pressure given data compound. Cylinder is formed by shrinking a tube with an internal diameter of 160 millimeters and thickness of 20 millimeters over another tube that also has a thickness of 20 millimeters. After shrinking, the radial pressure at the common surface is 8 megapascals. The compound cylinder is then subjected to an internal fluid pressure of 60 megapascals. Geometry of the compound cylinder. The compound cylinder consists of two layers. The inner tube has an inner radius of 60 millimeters and an outer or interface radius of 80 millimeters. The outer tube has an inner radius of 80 millimeters and an outer radius of 100 millimeters. Each tube has a thickness of 20 millimeters. Pressures acting on the cylinder. Contact pressure at the interface between the two cylinders due to shrink fitting is 8 megapascals and acts compressively on the inner cylinder. The internal fluid pressure acting at the bore is 60 megapascals. The external pressure at the outer surface is 0, since it is exposed to the atmosphere. Method of solution to solve this problem. We divide the analysis into three separate cases. The first case considers shrinkage pressure, acting on the inner cylinder only. The second case considers shrinkage pressure acting on the outer cylinder only. The third case considers internal fluid pressure acting on the complete compound cylinder. Case A. Boundary conditions for inner cylinder in the first case. Shrinkage pressure acts on the inner cylinder. At the inner radius of 60 millimeters, the radial stress is 0. At the interface radius of 80 millimeters, the radial stress is minus 8 megapascals due to the shrinkage pressure. Case B. Boundary conditions for outer cylinder in the second case. Shrinkage pressure acts on the outer cylinder. At the interface radius of 80 millimeters, the radial stress is minus 8 megapascals. At the outer radius of 100 millimeters, the radial stress is 0. Case C. Boundary conditions for internal pressure in the third case. Only internal fluid pressure acts on the entire compound cylinder. At the inner radius of 60 millimeters, the radial stress is minus 60 megapascals. At the outer radius of 100 millimeters, the radial stress is 0. Determination of constants A and B FOR each case. Constants A and B are determined using the corresponding boundary conditions. These constants are obtained by substituting the boundary conditions into Lame's equations and solving the resulting equations. Constants for each case for case A. The constants are A equal to minus 18.29 megapascals and B equal to minus 0.0658 megapascal meter squared. For case B, the constants are A equal to 14.22 megapascals and B equal to 1.422 megapascal meter squared. For case C, the constants are A equal to 33.75 megapascals and B equal to 3.375 megapascal meter squared. Stress equations using Lame's theory using these constants. Lame's equations are written for radial and hoop stresses for each case. These equations are valid within their respective regions of the cylinder. Based on the radius range of each layer, stress. Calculation across the thickness. Stresses are calculated at several radial positions across the thickness of the cylinder, starting from 60 millimeters to 100 millimeters. Radial stress and hoop stress are calculated separately for each case. Superposition of stresses then. Total stress at any radius is obtained by adding the stresses from case A, case B, and case C. This principle is known as superposition and is valid because the material behavior is assumed to be linear and elastic. Final radial stress. Distribution. The final radial stress is compressive at the inner surface and gradually increases towards 0 at the outer surface. This satisfies the boundary condition at the outer radius of the compound cylinder. Final. Hoop stress distribution. The final hoop stress varies across the thickness of the compound cylinder. The maximum hoop stress occurs near the inner surface and is significantly reduced compared to a single thick cylinder due to the beneficial effect of shrink. Fitting. Interpretation of results. The shrink-fitted outer cylinder introduces compressive stress in the inner cylinder. This compressive stress helps counteract the tensile hoop stress caused by internal pressure, resulting in a more uniform and safer stress distribution.